Lab 5, Choose Your Own Adventure, Spring Oscillations in One-Dimensional Motion. And the purpose of this lab is to observe one-dimensional motion of a spring mass system in which the mass oscillates along the length of a spring. And here are all the equations and constants. So the very bottom, the time period for a spring, calculating force net, calculating force of spring, gravity, change in position, change in potential energy, change in kinetic energy, kinetic energy, potential energy of the spring, potential energy of gravity, kinetic energy, fundamental principle, and then the gravity, the initial length of the spring, which we derived from the video, the spring constant, again, derived from information in the video I'm about to show you, the initial position, the mass, and the time period of the spring. And so in this video, spring oscillates up and down along a mass oscillates up and down along a spring. And so using that, knowing that this is about 0.7 meters and that the spring is initially at rest at that length away, you can then calculate using the time period, which we derive from here, this graph, and find about 1.54 seconds. You can rearrange this equation and solve for K, which comes out to 6.83 newtons per meter, or Newton meters. And the original length then you can also solve for at 0.123 meters. And so this is the calculation loop in order to calculate the position of the ball along the spring over time and the energy graph you get from it. And so the blue one is kinetic energy. You have the potential energy of the spring and the potential energy due to gravity, and they oscillate back and forth, and the total energy is equal to 0 in the system. Nothing is the energy is changing between forms of kinetic and potential. It's never actually leaving or entering, no new energy is leaving or entering the system after the object is put in motion. So you would expect that the change of energy is equal to 0, as this yellow line shows. And when we graph, the blue line is the model and the red line is the actual data extracted from Tracker. We find that they both match up so very closely, and that the model is a very, very good, accurate descriptor and predictor of the motion data of a spring oscillating in one dimensions. And so in conclusion, the system is the spring, ball, and earth, and the change in energy is equal to 0. New energy is put into the system, none's taken out, and energy changes from potential, kinetic, and back in the system. So the energy principle is satisfied, and the model fits the experimental data very closely. So it's a good model and accurately predicts the forces at play in the system.